Hello, good afternoon. How are you? And welcome back to Yebo Tutor. I hope that you had a fantastic week and you were having fun with your science classes. We know we are preparing for June exams now, so this is to wish you all the best in your tests. So what we will do here is to focus on some electrochemistry. What we've been trying to work through is to identify a question in a past paper and work through it. These are topical, so I guess by now you're aware of which topic applies to which question, and which question usually recalls which topic. So let me just see by the raise of hands or chats, right? So you can send in some chats if you benefited from the chemical equilibrium calculations. If you did, let's hop on to some electrochemistry. And we are working through the 2021 paper, the 2021 November paper. So this is paper 2 as usual, and we are looking for the chemistry questions. Right, so let's just see what is available. Grade 12, November 2021, the question paper. There are a few questions on electrochemistry on the first section, right? So let's just see what the first section has. I know it's multiple choice, so we'll have the answer somewhere there, so it might be easier for you to attempt. So let's just scroll all the way. Let's look for anything electrochemistry. Anything electrochemistry. Right, so that was some equilibrium. This was what? Yeah, this is some equilibrium constant calculation. Right, this is acids and bases, and conjugate bases, acids and bases as well. Okay, so we've got an electrochemistry question there. Right, so we will apply some principles on electrochemistry, and you will recall how you solve for these problems. So we have a question here, question 1.9. Let me also just scroll and see if we can create some space. Right, let's also look at it from here. So this is our question. It's an electrochemistry. By virtue, if you just look at it, you can tell, isn't it? You can tell that we are discussing electrochemistry now. So what do we have there? We have a voltaic cell. So the question reads as follows. The diagram below represents a voltaic cell. So this is a voltaic cell, and what we can see is that there is some zinc electrode which is immersed in a solution of its ions. So in this case, the solution is zinc sulfate. We also have a copper electrode, and it is immersed in a solution of its ions. So we have some copper sulfate solution. Then we have the terminals of the electrodes. The terminals of the electrodes. What's happening to these terminals? Can you see that these terminals are connected? These terminals are connected to a meter. Which meter is that? Which meter is this one? This is a voltmeter. This is a voltmeter. Now this is where you see physics and chemistry interlinking. This is where you see physics and chemistry interlinking. So we actually see some electrical measurement there. Okay. Then what is the last constituent? We obviously have our electrolyte, electrolyte, and another electrolyte there. Electrolyte. Which is in here, and then we have our salt bridge. Okay, so we have a number of things that are making up a voltaic or a galvanic cell, isn't it? Right, so we have seen the components of the galvanic cell, we have seen the metals, we have seen the electrolytes, and now let's find out what they want us to do with all this material. The question is, which one of the following correctly describes the movement of ions in the cell? which of the following correctly describes the movement of ions, right? The movement of ions in the cell, right? So by inspection, the movement of ions is being discussed between the following 2 points, X and Y. So the movement of ions is being discussed between the following 2 points, X and Y. So if there is a motion between the 2 points, it's either we have motion between X and Y externally, right? Or we have motion of these ions between X and Y internally, isn't it? So it will be necessary for you to appreciate that X and Y are just 2 points. And if this is an electrochemical cell, then there must be a complete path of motion of charged particles. Okay, so we're happy. Now we know it's in between X and Y, so those are the 2 points. The next thing is, they want us to describe the motion of what? Of ions. So let's see if there are any ions that are shown. Yes, we have the chloride ions, the sulfate ions, the copper ions, and the potassium ions. Okay, where are the chloride ions coming from? From the salt bridge. Where are the sulfate ions coming from? From either electrolyte. Where are the copper ions coming from? From the copper electrolyte, copper sulfate electrolyte. And then where are the potassium ions coming from? From the salt bridge. So we have identified the ions. We can see where these ions are. So let's just represent our ions in solution. Copper 2 plus is somewhere there. There's a sulfate somewhere there. And then in this other part of the electrochemical cell, then we have our zinc ions, and we also have some sulfate ions. Okay, and then the zinc solid is there, the copper solid is there. Now, how do we determine the direction of flow? We need to understand what's actually taking place in the electrochemical cell first. What is taking place? So we've already described that this galvanic cell has some solid material that is immersed in a solution of its ions. We've already identified the ions. The same applies on the right-hand side. So now, how do we identify the processes taking place? Whenever we have this metal dissolved in its solution of its ions, then there is bound to be a possible chemical reaction. The same applies to what is taking place here. So now that we have a complete path, right? We have a complete path. Charged particles can move in this part of the cell. Charged particles can also move through this part of the cell. Now, which charged particles will move in this part of the cell? These are just electrons, isn't it? So the electrons will be driven either from that direction or from that direction. So how do we determine which is which? How do we determine which direction our charged particles are going to move? Right, this is where the electrochemistry series comes in. Where can we find it? In the question paper. If you scroll somewhere further down, you will find a data sheet. You will find a data sheet. Okay, so let's see what's happening to this data sheet. Let's just see the data sheet for the electrochemical process. There we are. We have some standard reduction potentials. We have some standard reduction potentials. Okay, so as you can see this table, it shows you the standard reduction potentials in the form of increasing strength of oxidizing agents, right? Increasing strength of oxidizing agents. How about on the right hand side? Increasing strength of reducing agents. So now this is where you bring in your redox knowledge. Okay, so what is reduction? What is oxidation? Those are the two processes that will take place. So we need to compare our two materials. We need to compare our two materials. In this case, we have zinc in a solution of its ions. So zinc in a solution of its ions will dissociate or will be reduced. So let's see our zinc in a solution of its ions. What is likely to take place with zinc? This is the position of our zinc in the electrochemical series. Right. So any material that is below zinc is actually a reducing agent, making zinc the oxidizing agent. Any material that is above zinc is the oxidizing agent, making the zinc a reducing agent, isn't it? So let's see, our material in this case is what? Our second material is copper. So let's see where copper is found. There we have some copper. There we have some copper. There we have some copper. So of these two, excuse me, of these two, we said the increasing strength of the reducing agent is in this direction. The increasing strength of oxidizing is in that direction. So this is our oxidizing agent. In our case, our copper becomes our oxidizing agent. Oxidizing agent. Then our zinc becomes the reducing agent. Our zinc becomes the reducing agent. Why? Because according to the electrochemical series, our zinc is further down, isn't it? Using this part of the table, excuse me. Remember, you have another part of the table which is arranged in a different format. So you choose which you are comfortable with. However, the data are all the same. Right, so here we're happy. We've seen that, okay, our zinc is the reducing agent. This is our reducing agent. And our copper is the oxidizing agent. So, if zinc is the reducing agent, what is to reduce? To reduce is to what? Is to lower the oxidation state of the species that this reducing agent is working on, isn't it? So this is our reducing agent. So if it is our reducing agent, what is actually going to take place is it will donate some electrons. So our chemical reaction for the reducing agent is actually going to be in this direction. That's the only way our zinc can donate. So this means our zinc is actually dissociating from its metal state into solution by donating electrons. So what happens when it donates electrons? Then we have an excess of electrons on this terminal. We have an excess of electrons on this terminal. Right, so if we have an excess of electrons, these electrons are what will be driven. These electrons will be driven, isn't it? And we've already now identified that our cathode will, our material here will drive our electrons. So in actual fact, we're actually driving electrons from the anode material. Our electrons will be driven in that direction. As the electrons are being driven, then what is the expected motion of charged particles? It's obvious that our cycle is now in the clockwise direction according to this view. If negative particles are flowing clockwise. This must mean that we should also have negative charged particles flowing from y to x, isn't it? From y to x. And which are these negatively charged particles? Then obviously, when we are looking at the salt bridge, our chloride ions are supposed to move. So let's look at our options here. In part A, the option that is available is that chloride ions are moving from y to x. Does that agree with what we have? Yes. From y to x, we expect negatively charged particles of the salt bridge, which are chloride ions. So we're happy. The first option is actually correct. Let's look at the second option. The second option, sulfate ions will move from x to y. Sulfate ions, yes, we do have some sulfate ions. I've actually drawn them there. And we actually have some sulfate ions there. How would the sulfate ions move from x to y? It's either through the external circuit, which is not possible because only electrons will travel within a conductor. How about through the salt bridge? No, the salt bridge, there is no mixture of our salt bridge ions with our electrolyte. In actual fact, we put some wool there so that we actually do not have the charged particles that are traveling into the salt bridge. So in the end, we only have the ions to complete the path of the cycle. So this second option is out. Our B is out. The sulfate ions are not going to travel through the salt bridge. Neither are the sulfate ions going to travel through the external circuit. How about part C? Part C, we have copper 2+, moving from Y to X. Copper 2+, these are the ions, and we've already seen that this is the chemical reaction that is taking place. Our copper 2+ are being reduced. This is the oxidizing agent. So the copper ions are actually accepting electrons and solidifying. So our copper is actually growing on this electrode. So this means we do not have motion of our copper ions. How about our potassium ions? Potassium ions must obviously move from what? From X to Y. Potassium ions must move from X to Y in the direction of the conventional current. However, they say from Y to X, so Y to X is the wrong option, leaving us with our chloride ions. Does that make sense to you? Did you see what we did there? All we did was to look at the build up of our galvanic cell, identify what is actually taking place at each electrode, refer to the electrochemical series, isn't it? We refer to the electrochemical series to identify the substance or the material or the metal that behaves as the oxidizing agent or the reducing agent. It is all relative, right? So we are done with question number 1.9. Any questions on that one? Any questions on that one? Let's hear you give us your questions. We've seen a few things now. We have worked on a galvanic cell. Let's look at the next question. The next question is the opposite. The diagram below represents a cell that is used for refining copper. This is a cell that is used for refining copper. So what we have in this cell are the following. We have a power supply unit. So it's either positive on this terminal, negative on that terminal, or negative on that terminal and positive on that terminal. Then we have some metal X, labeled X on this left hand side of ours. We have a copper sulfate solution. Then we have impure copper. We have impure copper. Now, we already know that there's a tendency of the copper dissolving into its solution of the ions, isn't it? So this is our solution, copper sulfate solution. In there we have it. So the diagram below represents a cell that is used for the refining of copper. So in this cell, you actually force the electrochemical process. You actually force the electrochemical process using a power supply unit. The energy change is now from electrical to chemical energy. In our previous case, the energy change is actually a chemical energy that determines electrical energy, or that converts into electrical energy. Right, the question now is, which one of the following statements is true? Which one of the following statements is true? Right, so if we were to purify this copper, with a power supply unit, before we even look at the statements, let's try to reason out the process. Right, so if you are to power this, it's obvious that within the solution, you have some copper 2+ ions and some sulfate ions. Now, let's just make that a proper subscript. Now, if we have our copper ions in solution and our sulfate ions in solution, so this is aqueous, and we want to purify, isn't it? We want to purify. This means we should create a situation where the ions that have been put into solution are actually driven towards an electrode that is not the impure electrode. We want, in other words, the copper to accumulate here, isn't it? We want the copper to accumulate here. How are we going to do that? We will need to attract these ions to the other terminal. So therefore, we need to have a negative terminal applied on the left-hand side. That way, if we drive a current in this process, we already know the electrode potential for the what? For the solidification of copper, or for the reduction of copper from solution onto the other electrode. So obvious, we need this to be the anode and that the cathode. That way we can then change this impure copper as we force it to dissolve into solution using the electrical energy. We can have all the copper ions now accumulate on the other electrode, and therefore we have purified the impure copper. Right, so which one of the statements is true? Number one, statement A says X is made of platinum. X is made of platinum. If you put platinum there, we are going to have all our copper just falling into this material, into this solution. We actually want it to stick there, so you can actually put a copper electrode. How about the mass? Obvious, the mass here increases, isn't it? As the copper accumulates on electrode X, the mass of electrode X increases. How about the third statement? X is the electrode where oxidation takes place. What is taking place? We said reduction of the copper ions as they accumulate, hence the purification. That's the process, isn't it? So here, X is the electrode where reduction takes place. Then D, X is connected to the positive terminal. No, we cannot connect this to the positive terminal, otherwise there's no way we can extract the copper ions so that they can accumulate on some electrode as pure copper. Okay, so which electrode reaction are we going to consider for this process? The copper solidification potential is what will, so this is what is taking place at electrode X. So we just have the copper 2+ ions reduced to become copper solid, and this is aqueous. Okay, so that is the process that has been taking place, and now we have our copper solid accumulating on the X. Okay, does that make sense? I hope so. So this was a matter of just selecting the correct option. Right, so let's move to the question that has a number of questions. We know that there are full free response questions here. So let's just scroll so that we see what's available. Right, there we go. So we've found the second question, free response question on electrochemistry. Free response question on electrochemistry. Right, so this question reads as follows. This is question number 8. The table shows two half cells, A and B, used to assemble an electrochemical cell under standard conditions. So in half cell A, we have copper with an interface of the copper metal. In half cell B, we have silver ions with an interface with the silver solid metal. Okay, so which type of cell is this? Which type of cell is this? We have been given two half cells. The interface, as we can see, is an interface between copper ions and what? And copper, the metal. The same applies another interface between silver ions and the silver metal. So we are obviously looking at a what? At A, is it a galvanic or an electrolytic? Is it a galvanic or an electrolytic cell? This is obviously a galvanic cell. So let's just attempt this question for the galvanic cell. So let's just draw it. Let's just draw it because we've already seen some example of a galvanic cell, isn't it? We already saw an example of a galvanic cell. So let's just draw this one and see what's available. So let's draw something like that. This is our cell A. So let's call it cell A. Then we have another cell here, which is our cell B. Let's call that cell B. The next thing is to immerse our copper. So in cell A, we have our copper material immersed in this solution of its ions. So we've not been given the solution of its ions. So let me just say Cu2+, right, in half cell A, and this is aqueous. And this is our electrolyte. There's our electrolyte. Let's just color it So we can see, okay, that is what is taking place there. Okay, so we're happy. We can see our electrolyte, and this is our copper aqueous solution. The interface is in between the copper aqueous and the copper solid electrode. That's our copper solid electrode. So we can then create some path to our, so you can choose, right? You can choose to have an ammeter, you can choose to have a voltmeter. It depends with what you want to observe. Do you want to measure the current flow or otherwise? On the right hand side, we have half cell B, in which we have silver. So let's have our silver as the other electrode. We know that it is within a solution of silver ions, Ag+, and these are ions in aqueous solution. So let's also draw that solution of silver ions. So there we have some solution of silver ions and something at the bottom there. Now we're happy, right? So let's connect the cell. Let's finish up the cell. And we have our cell there. What's left? What's left? You tell me, what's left? We are making up the electrochemical cell that is composed of a copper solid material and then a silver solid material as the electrodes that are immersed obviously in a solution of their ions. So you tell me what's left. What's left on this electrolytic cell? What's left? What's left? What do you think? We need something. What can we put there? You can even compare. You can even compare. Look at this. What's left? Tell me what's left. What is missing? What is missing? Right, I hope you've identified what is missing. What is missing from our electrochemical cell is a salt bridge, isn't it? We need a salt bridge. So let's just look for some other color to make our salt bridge. So our salt bridge is obviously to be immersed somewhere there. So we'll draw it like this. And what makes up a salt bridge? We need some plug, right? We need some plug right there. So that's our plug, and we can use some wool or some cotton as our plug. Then we need a paste of the electrolyte. So you can use, for example, what you see up there is KCl. You can also use NaCl, which is just our salt, common salt. Right, so that's our salt bridge, and I've just put in salt, the salt that we know as our salt. So that's our galvanic cell, electrochemical cell made of those two. So let's also finish up this diagram so that it looks as scientific as we need it to be. That's our meniscus, and on the right hand side the same must apply. There we are. So we are done. We've got our salt bridge. So let's just label that as the salt bridge. Right. So we can now attempt this question. We can see what's happening. We can tell that we have an electrochemical cell, cell A and cell B. We have seen the according to the given information, isn't it? According to the given information, we've seen what to put in cell A and in cell B. So that's our electrochemical cell. So the next question, the first question actually, according to this set, reads as follows. State the energy conversion that takes place in this cell. State the energy conversion that takes place in this cell. So that's our first question, question 8.1. Question 8.1. So for question 8.1, what is the energy chain? What is the energy conversion? Energy conversion. What did we say we have here? Do we have, remember this is an electrochemical cell, right? This is a cell. We are actually producing electrical energy. So we are starting from chemical energy to electrical. So you can call it chemical potential energy, to electrical potential energy, isn't it? It's potential energy in the first place. So we have chemical potential energy and then electrical potential energy. That is the energy conversion chain. So you can even see something like that in this interesting, let's just see if I can find the animation, energy changes and forms. So this is what you can do. You can actually visit this link and see what's happening here. Energy is being converted in one of the cells. We are converting chemical energy to electrical energy. In the other cell, we were converting electrical energy to chemical energy when we were purifying some copper. Right, so different systems will produce different types of energy. So just check this one out, right? Just check this one out. I'll copy this link and share it with you. So check out these examples of energy conversion. Energy conversion. So check out this. Let's just see if that is spelled out correct. So let's just say this example of an energy conversion chain. Right, so let's share that link. There you have the link. So can you see something here? You can, we have someone here who is representing any one of us cycling, isn't it? So when a person cycles, we can give them somewhat some energy to start cycling. When they cycle, if we attach their bicycle, one of the wheels are attached to a generator, then their mechanical energy, isn't it? Their mechanical energy will be transferred to rotational kinetic energy, isn't it? So that motion, that force that they're applying through some distance as they are cycling, isn't it? They're changing all this food into what? Into mechanical energy. So we're going to see that mechanical energy in this legend is gray. Then you have electrical energy in a, it's not a, let me call it blue, right? And then we have thermal energy, red. Then we have yellow, light energy, and then chemical energy, green. So if this person has eaten, can you see that they store some chemical energy that is from the food? So let's start to make them cycle so that their chemical energy is converted to what? To mechanical energy. And that mechanical energy is used to turn this generator until it changes from mechanical energy to electrical energy. And that electrical energy, as it is applied onto this heater here, it is converted to what? To thermal energy. and our water absorbs the thermal energy, and then we can release it. So let's start cycling. Look at that. Look at that. It's cycling, right? Look at that. Look at that. It's cycling, and we have conversion of chemical energy to mechanical energy. That mechanical energy is now being converted to electrical energy, right? Electrical potential energy. Then it is converted to some thermal energy inside this water bath. And that water continues to rise in temperature. So we can see that there is a temperature gauge here that indicates that all this thermal energy that has been absorbed is actually leading to motion of these particles of water. And look at that, it's now boiling. And look at our person. Our person, it keeps losing their chemical energy. So this is an example of a chain in which energy is converted. In our case of an electrochemical cell, our chemical energy in here is what is actually converted to electrical energy. This is why you can put an ammeter to conduct the current and hence measure the current that is being generated, isn't it, by the chemical reactions in there. Or you can actually put a voltmeter so that you can just tell the potential difference of the whole cell. So we've already identified that the energy conversion chain here is from chemical potential energy to electrical potential energy. Any questions on that? Any questions on that? Please feel free to share the questions so that we can discuss. Okay, so let's just try to see what will happen now. Our person, as they are losing all the energy, can you see they now want to be fed? So this one is saying feed me. Why? Because they've exhausted all the food within their body. Okay, so we are now free to move to the next step, which is question number 8.2. Question number 8.2. The question reads, calculate the mass of silver nitrate AgNO3 used to prepare 150 cubic centimeters of the electrolyte solution in half cell B. We've been given some information. In actual fact, in half cell B, the electrolyte solution is made of silver ions and some nitrate ions. So this is what we actually have in this second cell, cell B. So cell B is actually AgNO3, silver nitrate, electrolyte. This one we do not know. We've not been told, isn't it? We've not been told what it is. So if this is silver nitrate, we can maybe hope that this is copper nitrate as well. But the whole idea is these two half cells are actually made of a metal that is immersed in a solution of its ions. Okay, so we now have our silver nitrate as our electrolyte. So we now know what it is. So they want us to find the mass of the silver nitrate. So to find the mass of silver nitrate, AgNO3, what can you do? How can you find the mass of the silver nitrate? How can you find the mass of the silver nitrate? First of all, the data that have been supplied are the following. The volume is 150 cubic centimeters. That is the volume of the electrolyte solution. So in here, if we had a measuring cylinder, and these are the graduations of the measuring cylinder, it's actually at 150 mils. So that's 150 cubic centimeters. So what is this? Remember our volumes. The moment we are working out our chemistry calculations, we need our volumes to be in dm cubed. So how many liters is 150 mils? So that would be 0.15 dm cubed. Next, we want to find the mass. So to find the mass, I'm sure you still recall that there are some chemical calculations that we did before, which included that. However, if you've forgotten, this is what you can do. Just scroll all the way down this question paper, you will find the data sheet. I've already shown you part of the data sheet when we were looking for these electrode potentials. So let's just scroll and look for some formulae. There we have it. So these are some formulae that are provided in the exam. So you can actually pass this exam because there's some formulae that you actually can use directly from the exam paper itself. Right, so let's see. We want to find a mass, so we can use the equation for the number of moles, and we also can use that number of moles there, right? So if our concentration, so using the equation, concentration is equal to number of moles over volume, where this number of moles is actually given by the mass over the relative molecular mass, and then we multiply by 1 over volume. Can you see that we are coming up to this equation? So since we have that, we want to find a mass, so this must imply that the mass is equal to the concentration multiplied by the relative molecular mass multiplied by the volume. So this is the equation we are going to use. The mass of the silver nitrate is simply found by multiplying the concentration by the molar mass by the volume. So let's now find the mass. So the mass, okay, so where is the concentration now? Where can we find the concentration? How can we find the concentration? Please tell us. How can we find the concentration? How can we find the concentration? If you would like, take your time to look for it. Let's look for the concentration. Right, where is this value found? Where is this value found? Have you found the concentration? Have you found the concentration? We want to calculate this, but we need the concentration. Right, I'm sure by now you have seen, that we are at standard conditions, isn't it? We are at standard conditions. I cannot see a table that has our standard conditions, right? Standard conditions, can you see that? Right, so that's our standard pressure, standard molar, gas, and so forth. Okay, so we are not given the standard concentration, but I'm sure you still remember now from the theory that when we are calculating all our values at, remember they've said this cell is under standard conditions, so which means the concentration is actually 1 mole per dm cubed. That's the concentration. The molar mass, what is the molar mass? This is obviously in grams per mole, and then multiplied by the volume. We already have the 0.15 dm cubed. Right, so what is the molar mass? What is the molar mass? We have silver nitrate, there we have it. So what is the molar mass of silver? Let's look for the periodic table. Let's look for the periodic table. There we have it. Where is silver? Silver is here. There we have it. Silver has a molar mass, remember, on your periodic table. This is our approximate relative atomic mass, isn't it? This is our approximate relative atomic mass, so we will use that. So that's a 108 plus. How many nitrogens? One nitrogen. So let's look for the nitrogen. It has a mass of 14. How about the last? We have 3 oxygens. So it's 3 multiplied by oxygen 16. 3 multiplied by 16. So our calculation is going to become, let's just look at the units. The units per dm cubed and dm cubed cancel out. Next is grams per mole, and that mole cancel out. So in the end, we actually have our calculation in grams. So this is 1 multiplied by, what is 108 plus 14 plus 3 times 16. So what is 108 plus 14 plus 3 times 16? Let's calculate away. 108 plus 14 plus 3 multiplied by 16. So multiplied by 170 and then multiplied by 0.15. That was dm cubed, so we are left with grams. So basically we are closing this bracket. On this part we have a 1 multiplied by that, then multiplied by 0.15 dm cubed, so that in the end we are getting 25.5 grams, isn't it? 25.50 grams. That is the mass of the silver nitrate. The mass of silver nitrate. So what was the important thing in this calculation? The important thing in this calculation was to remember standard conditions. In electrochemistry, when we make a galvanic cell, we need to compare it, and we need to compare these galvanic cells consistently. So we put everything to standard conditions. The concentration is 1 mole per dm cubed. 1 mole per dm cubed. The standard temperature, I'm sure you already know it, and the standard pressure, I'm sure you already know it. Right, so basically this one is also an important figure. Right, so we are done with question 8.2. Any questions on that? Any questions on question 8.2? Okay, so we are done for time. Let's just try to rush a bit so that we can maybe get another question on board, 8.3, and then we can move to 8.4. Okay, so we can finish that next week, but let's see what 8.3 has in store for us. 8.3. So question 8.3 states the following: define the term reducing agent. Okay, so I think we can actually do 8.4 because this is just a definition. What is a reducing agent? What is a reducing agent? First of all, what is reduction, isn't it? So this is now the topic on redox reactions. So what is reduction? I'm sure you already remember that. Reduction is a drop in the oxidation number of a certain species, or reduction is when a species or when a certain ion receives receives an electron, and then its oxidation number or oxidation state reduces in the negative direction, isn't it? Okay, so a reducing agent is the species that will cause reduction, isn't it? Which means a reducing agent simply donates electrons. When it donates electrons, it drops the oxidation state of the other species. So a reducing agent is an electron donor. An electron donor. An electron donor. That's a reducing agent or agent. Any questions on that? So let's try to move a bit fast now. 8.4. Question 8.4. The question is, write down the name or the formula of the reducing agent. Wow. I think I would like to give you this one to work it out. Why? Because if you remember in our first question, right, where we had an electrolytic, we had a galvanic cell. We actually looked for the reducing agent. Did you see what we did? So scroll back either on this video or go to your notes or whichever way you recall how to work this out. And you answer question 8.41. So in actual fact, when we meet next week, we'll take it from question 8.41. You should already have the answer for the name or the formula of the reducing agent. So you just go to the electrochemical series and do some things. You can already see what we are working with in this electrochemical cell. So you know that this is our electrochemical cell. So within this electrochemical cell, which is the reducing agent? Which of these is the reducing agent? So you try to figure it out and work it out. We've already shown how you can do that. So use your skills now. The next part would be the balanced equation for the reaction that takes place. So let's see you give us the balanced reaction. Remember, when you already have the reducing agent, you now know which of the species is reducing the other, right? So if you've identified the reducing agent from the electrochemical series, you already know which one is being oxidized. In other words, you know the direction of the half reactions that will be considered. Right, so basically this is it. I think we're done for today. I hope you can have some fun working out the rest of the questions. When we meet next week, we need to finish up this question. So just pop in or drop in your questions that are related to this calculation or this topic. Thank you very much. This is the end of our TUT session today. I was going to have some fun with us with this simulation, so we will use it next week, right? Because we don't want to get the answer before we actually work it out. So we will use it next week. We will also look at this one. It's a very nice simulation as well. So we'll use this simulation again next week so that we can understand our half cells. So this is the end of our TUT. Thank you very much. Have a fantastic weekend and week, and all the best if you are writing and when you write. Goodbye.